All right, guys. It's 4 o'clock. Let's get started. So I'm recording. Let's go to the uh, bright space and let's see where we are. So we are here. We're wrapping up RSA today. That doesn't mean we're wrapping up asymmetric encryption. There's three algorithms actually that we cover for asymmetric encryption. We've only covered one so far, but the most important one, of course, which is RSA. We still have Diffie-Hellman, which is actually kind of a short idea, but actually the original work was Diffie-Hellman. So we'll go over that one as well. It's a type of key exchange. And then, of course, elliptic curves we will cover as well. And yeah, so we will look at that. So if you remind, and so that's, yeah, as you can see, RSA. So the plan today is to wrap up RSA, just a few, I have some slides to kind of I usually summarize the topics with slides. And then also I have a few last notes. This is more like details at this point, little interesting things here and there, but we have covered the gist of the algorithm. So today I'm just going to wrap that up with the slides and um, the theory. We're still going to be using it a lot because actually we've only used RSA for confidentiality when we're sending the secret message. But there's this whole other area of RSA, like we've only covered like half of it. There's the whole other half of it, which is when we reverse RSA. And instead of providing confidentiality, we want to provide authentication. So this is the whole idea of digital signatures and all of that, certificate authorities. So there's quite a lot there, right? And so we're just going to flip the script, but we're going to start that today as well. As I wrap up kind of like the algorithm, we're going to start to think about that idea. Okay, so that's, as I said in the slide. Just a few reminders before I start. We're currently on week 10. So this is week 10. That's right. And the semester has 16 weeks, so you really only have 6 weeks left until the semester's over, right? So that means we have exam 2 coming up also. That's going to be on week 12, and we're currently on week 10. It's going to be a Tuesday, similar to the previous exam. You can expect the same. Everything applies. Closed notes, you're allowed your cheat sheet. And it's comprehensive because obviously everything ties together, right? So, but obviously there will be a lot of questions about RSA and asymmetric encryption. Okay, so like I said, I'm wrapping up this week. Thursday, maybe today, if time permits, we'll continue with PyCryptoDome. If you remember, I covered AES, encryption and decryption, but we're actually using PyCryptoDome for a lot. And so we need to cover a lot of the principles because you will have a homework that you need to demo, if you remember, and you will be using PyCryptoDome for that. The scavenger hunt is coming up. Could be week 12, could be week 13 or so. It'll happen for sure when I think you guys are kind of ready for it. So there's no rush, right? And then, like I said, once the exam passes, we still have Diffie-Hellman, elliptic curves, and then we move into the applications domain. So if you think about it, what is cryptography used for beyond encrypting things, right? So, blockchain, a little bit of the theory there. Actually, you use it for antivirus scanners. You can defend against denial of service attacks. And of course, we'll look at PKI, HTTPS, right? So how does that work and everything? So those are kind of the topics. All right, so things for you to consider. 6 weeks left. Start studying for the exam in 2 weeks on week 12. Another important thing is the term project. You have less than 6 weeks at this point to complete your term project. Remember, you have the final exam on finals week, and project presentations will be the week before finals. Got it? You can work in a group. We've talked about this. Groups of 3. Just pick a topic related to cryptography. You need to explain it and demo. Now, you can code if you want, or you can just install a program and configure it in Linux, something like that. Any questions for me? Right. All right, great. So now, yeah, like I said, I have some slides and I have some notes on RSA, and hopefully that'll wrap up those topics, and then we can move on to PyCryptoDome. The next topic is likely to be Diffie-Hellman. That could be next week, so that may also be in the exam, um, the second exam. All right, so let's go over here. So this RSA. So I have two sets of slides that I'm going to download. These two PDFs are just the notes that I write in class. So we've already covered this, everything about like GCD and RSA, all that is in there. But I do have these kind of this set of slides and this one, which are kind of wrapping up some of the ideas and actually introducing some new things. So I want to start with that today. And then we're going to move into the notes, just a few little, as I said, little key final ideas or comments. And then from there, we'll probably have time to continue with PyCryptoDome. So we'll hop on to the virtual machine. All right, so I believe it's this one first. Let's start with that one. Don't know what that is. What is that? Try that again. Oh, it's doing an update. This looks different, right, from what I use. This is why everyone loves Windows, right? Because it always wants to update. Always. Okay. Okay. Type of PowerPoint, maybe. All right, so let's these are not very long. So they shouldn't be, and it's kind of a summary and then the introduction of yeah, and the introduction of RSA for authentication, which is actually like it should just be a fascinating thing. Like I always, with encryption and everything, the mathematics of encryption are just so fascinating, right? So like you can do these amazing things with just some tricks of algebra and things like that. Okay, so yeah. So if you remember, we RSA, right? So the name came from the algorithm that was proposed by Rives, Shamir, and Edelman in the 70s, I believe, to solve the problem of asymmetric encryption. Historically, before Diffie-Hellman, a bunch of scientists had figured out an idea, but this one was much better than Diffie-Hellman, although we can use Diffie-Hellman also. And we'll see that algorithm probably next week. So the RSA encryption scheme provides asymmetric, as you know, public key encryption. The public key consists of two large integers, e comma n, right? And the private key consists of two large integers, d comma n. Remember that, note that the second number n is the same in both, right? And the three numbers e comma d comma n are related in a special way, which, as you have seen, requires mathematics. Okay. The crucial point is that, and this is, I'm wrapping up this right now, but the key ideas, the crucial point is that n is guaranteed to be the product of two prime numbers, right? And you know this, right? So n equal p times q for two prime numbers, p and q. If you know e and n, and you found the factorization of n into p and q, you can compute d easily. So the security of RSA requires that factoring of large integers is difficult, right? You guys have actually done this, right? So you've seen this now with the quantum computer simulation, or you've seen this with FactorDB, as we did in the quiz. So this is key, right? So this is why everyone is so worried about a quantum computer. The moment that arrives and everyone starts breaking, all of our encryption, it's going to be a serious problem, actually. I always make the joke, let's say that I'm some kind of researcher and I'm not even using a quantum computer. Let's say I'm using AI or something, and I find a way to break RSA to factorize n. What do you think I should do? What are my options? Should I publish this? It's 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 I mean, think about all the disruption that would cause in the world. It's probably easier just for people to like bury me somewhere. You know what I mean? Think about it because of all the, military systems compromised, banking compromised, your YouTube compromised, right? So everything would be compromised because everything we do relies on that key exchange. Do you see that? And then there's elliptic curves, but elliptic curves are kind of related to this as well. You see that? So there's a connection. And so yeah, it's a big problem. But anyway, so far no one has broken it that we know of. So you can see here actually the comments are very important. So the security of RSA requires that factoring a large integer is difficult. And when they say large, they are not kidding. Now, you guys already saw we use keys that were very big in the last homework assignment. I think that 4096 never processed. Now, granted, that was on the VM and everything, but still, and written in Python versus C. But still, the key is really big. So today, RSA implementations might use 4096 bit number for n or even bigger. Now, this is important. No one currently knows how to factor numbers of that size quickly, which is to say, before we, our planet, are long dead. So obviously, we can factorize smaller numbers. We did that with the Qiskit, right? And that Qiskit, although it simulates a quantum computer, obviously there is no quantum computer there. There was a normal laptop. So we are, through algorithms, able to factorize, but just not as big as what they're using right now. So it would take, basically a long time. So RSA seems pretty secure. However, no one has proved that it's impossible to factor numbers quickly either. See, that sometimes in mathematics, you have these things called proofs, right? And so you'll have a proof of one thing or the other. So at some point, somebody thought, okay, let's find a proof that says that it's impossible to factor numbers quickly either. But no one has found that proof. So it may be possible. Do you see that? So that you don't have that guarantee. So RSA may be broken someday. Maybe it'll be broken by you guys if you become, researchers in this field or with quantum computers, who knows, right? But it's a very serious thing if that ever happens because it would affect the economy. So this is kind of a joke, but imagine you have to break this massive encryption. They've got 4096-bit RSA to get some kind of a password. It's probably easier just to hit them with a wrench and get the password out of them. You know what I mean? So you have to think. It's such a difficult problem, right? It's a difficult problem to do that, to break RSA. All right. And that's kind of, so, wrapping up some of the ideas, I will introduce here digital signatures. So this is now a new topic. We are not, it's the same algorithm, same code, same everything. We're just going to flip the script, right? So that's all we're doing. So remember, the scenario is we've got Bob and Alice, and each of them in asymmetric encryption have a public and a private key, right? And we've been using the public key to encrypt, and then it can only be decrypted with a private key. Now we're going to kind of flip the switch, and we're going to, let's say, encrypt with the private key, and that gets decrypted with the public. Do you see that? Okay, so think about that idea, right? That sounds strange. You're encrypting with the private key, and then you're going to decrypt with the public key. What's the problem with that? Everyone has the public key, right? Because it's the public key. So what does that mean? If you encrypt something with the private key, everyone can decrypt it. What's the use of that? Exactly. So it proves authentication because only your private key could have generated that. Do you guys see that? And that's the central idea of authentication on the internet. Everything that happens, as far as authenticating that this is Chase and that's Amazon and this is Netflix, happens because of this idea that several parties, in fact, use their private key to encrypt something, and only the corresponding public key to that can decrypt it. So if I sent you an exam, right, and then you have a friend that also wants to play a joke on you and they send you an exam, how do you know which exam to use? Do you see what I'm saying? So you want to use, I'm going to have my public key here, right? And so you're going to verify. You're going to use that public key to run it with your friend's message and also with what I said. So only mine should authenticate. Got it? So that's the idea with this. Yeah, and in a nutshell, right? And but obviously there's always details that we have to look at. So let's take a look at some of these details. And let's give a scenario. So the best scenario is probably contracts, like electronic contracts. You actually, when you use authentication, you're actually going to use integrity and authentication together because it only works. You can only get it to work that way. But actually, it makes a lot of sense because you already understand integrity. You already understand hash functions. So what do you know about hash functions? You take a variable length input to produce a fixed length output. And if you just change one bit of that file, what happens to the hash value? Totally different, right? So that's integrity. So now we're going to study the process of how to authenticate things such as a contract. Okay, and you guys will be doing this probably in one of the next homework assignments and also on the demos and things like that. So, on the practical exam, I could give you two keys, one to mislead you and one is the correct one. And obviously you may need to check, okay, this is the public key that I was given. Which one of these two keys should I use? If you pick the wrong one, it could take you in a detour that cost you 20, 30 minutes of your time. You see what I'm saying? So that's why that is very useful. So suppose Alice sends a contract agreement to Bob. To avoid legal troubles, we'd like this communication of contracts to have the property of non-repudiation. Bob should be assured that Alice can't back out of the deal by claiming she never sent the contract. Can you imagine if we lived in a world like that, right? So you enter into contracts and then people are just like, no, because they're digital, right? So they would just withdraw. So that's the principle, by the way, of non-repudiation when they say they didn't do something. Likewise, we want the property of integrity. Alice should be assured that Bob can't modify the contract and claim that the modified version is what Alice sent him. Okay? And we know that integrity does this. So we're just going to use these two steps together to achieve what we want. So there's a nice technique called digital signature that provides these guarantees. Alice, and here, let's take a look. So Alice simply computes a hash of the contract agreement, right? So you take the file, take the hash of it. And then notice, you don't even have to encrypt. This is, like elegant, right? You don't even have to encrypt the file itself. You just encrypt the hash. Think about that, right? So Alice simply computes a hash of the contract agreement, then encrypts the hash with her private key and sends the result. That's usually called the digital signature, which is the electronic signature, along with the contract to Bob, right? There's nothing of confidentiality here. You're fine with everyone seeing the contract itself, right? So that's not a problem. So we're only concerned with integrity and authentication, but not confidentiality. Although you could add that if you wanted to. So anyone can take the contract in this scenario, hash it, and compare the result with what you get when you decrypt the electronic signature with Alice's public key. Do you guys see that? So that digital signature that you got that was generated via private key of Alice can now be decrypted with the public key of Alice. Everyone can do that. And then that gives you what? The original hash value. So now you just take the file, hash it. If it hasn't been modified, those two things should match, and that's it. So usually in a digital signature, that's what you do. You just get a true or false, right? Or pass or fail. And so that's going to be the process. And that works perfect in the internet, right? So the internet, imagine code running. So the code just says, okay, check the signature, true or false. If true, you're allowed in. If false, you're not allowed in. Okay. So if it matches, so what you get when you decrypt the electronic signature with Alice's public key. If it matches, then the contract must be exactly the same as what Alice sent, because Alice must have sent it, because only Alice can encrypt something that decrypts properly with Alice's public key. So the contract cannot have been modified because the hash value would have changed. And as we have seen many times, even just one bit of the binary file changes the whole thing. Any questions? Do you guys see this? So you can see it's pretty much the same mechanism, but kind of like in reverse. So asymmetric public key encryption is almost magical. You create security out of insecurity, right? Just by creating these public and private keys and agreeing on a few things. However, now this is important though. However, there is still one weakness in the system, and that's like the last weakness, which kind of goes back to the first week. Remember what I said in the first week? If you wanted to agree on a secret key, you had, and without knowing algorithms, what did you have to do? You had to go to a coffee shop, sit down, and like exchange the key, right? That's not practical for the billions of people on the internet. However, it is practical for just a handful of companies. So this last step is the essentially meeting in a coffee shop and agreeing to some things. Okay, so let's see how that works. So let's talk about it. So asymmetric encryption is almost magical. You create security out of insecurity. However, there is still one weakness in the system that's fundamental. So for instance, you see on a website something like, hi, I'm Bob. This is my public key, right? And you can see it's a public key. This is the E exponent, and that's the N over there, right? So it's a public key. So what's the problem with this? So the problem is, how do you know that that public key really belongs to a guy you know as Bob? Do you know what I mean? Like, how do you know? Like, let's say that you want to go to Chase Bank to do some bank transaction, right? Somehow this man-in-the-middle attack sends you to something that looks like Chase, and they say, hey, I'm Chase, here's my public key. Do you see that? But is it really? Right? It could be a man-in-the-middle attack, right? We all understand this. Because you could have also gone in another direction to the actual Chase, who also says, hey, I'm Chase, and here's my public key. And that's the trusted one. So what do you need to do to solve this problem? You need to have what the internet uses, which is the certificate authority, the CA. You may have seen this. We're all familiar, I think, with VeriSign, right? We've all heard of VeriSign. Obviously, there's many more today, like Google, and all the big companies have their own CAs, but they're essentially the same thing. You pay them tons of money for them to create a private key, and what do? They sign something for you with their private key that can only be decrypted with their public key. But they are trusted. So this is a highly regulated industry, and it's just really not for like all of us, right? This is for the big companies like Chase Bank, Amazon, things like that. Do you guys see that? So for instance, um, let's say that you're Amazon, right? And you want to do e-commerce. So what do? You send your executive to the office of VeriSign and you show up with like legal documents to prove that you are in fact Amazon, and then they'll do the whole process. Do you see that? And then what happens is VeriSign then will use their private key to create a digital signature for you. Their public key is also very trusted. And so now it falls on the web browsers to do the last step. So the web browsers hold VeriSign's public key. Do you see that? And that's how the whole process works. So whenever you go online, we don't see this, right? It's behind the scenes, but you open, your favorite browser, right? Mozilla Firefox. Well, Mozilla Firefox is also regulated, especially in this. It has to have this done really well. This needs to be very secure. As you know, in your software assurance class, I'm sure you've seen, there's a lot of security mechanisms that need to be incorporated in the browser. And this is key. The browser holds the public keys of the certificate authority. Do you guys see that? And so that way, okay, VeriSign's public key is here. Now Amazon or Chase or Bank of America or something like that, Wells Fargo, they go to the office of VeriSign. Here's my public key, and I am for sure Amazon. Sign it. So VeriSign comes in, signs it, issues the certificate. Their public key is already in the browser of Amazon. So whenever you do the whole transaction, you get that key that says this is from Amazon. Okay. And by the way, it was signed with the private key of, Amazon, and it was signed with the private key of VeriSign. So now the browser does what? Checks, right? That it decrypts with the public key. It checks the integrity and that's how it works. Does that make sense, guys? Is that clear for everyone? So that's the certificate authority. That's what this is talking about. So it's the last step, which has to be like humans in the loop to check so that people aren't pretending to be. So if you go, you can be assured in a sense that if you get a man-in-the-middle attack and you go to a thing that looks like Chase, you're not going to get scammed. You see, because when you go there, what's going to happen? Okay, they're pretending to be Chase. Here's my public key of Chase. So you're like, okay, great. But when you grab that key and the browser tries to run it, they're going to check it with VeriSign's public key. And guess what's going to happen? It doesn't check out. So that's why it tells you this is not trusted. And you get that whole get out of here message or something like that we've all seen, right? Are you sure you want to go into this website? It doesn't check out. Otherwise, we get that little lock, and it just means that everything worked in the background. All right, we will do a lab like that. So the funny one, the funny trick there is that you will become your own certificate authority because you can do that with OpenSSL, no problem. And it's not by default in the browser. So what you will have to do is you will become your own certificate authority. You will have your own certificate authority public key. You were loaded into the browser as a known public key. And then when you start signing other things with your private key, it'll check out as being validated by you. This is a lab that we'll do when we do applications. So it's in about 3 or 4 weeks. Okay. All right. So, but that should be pretty clear. All right. So this is the idea. So, but how do you know that the public key really belongs to the guy you know as Bob? Well, you can be assured that if you encrypt a message with this key, only the key's owner will be able to decrypt it. How can you be sure that the key's owner is really Bob? If you trust a website on which the public key is posted, you might be comfortable. But at the end of the day, you have to trust whoever is presenting this key as belonging to Bob. And that trust is a security weakness that needed to be addressed. And so the solution is the certificate authority. Okay? All right, so that's that set of slides. Are there any questions on that idea? All right, so seems like it made sense. We'll definitely come back to that quite a bit. So let's move on to the other set of slides now. If I can close this one. Let's do asymmetric. I think this one just summarizes more of the ideas of RSA as we're kind of wrapping up RSA today. Okay, let's do that. Okay, so yeah, so just wrapping up. So as you know, we've talked about confidentiality, authentication, integrity, and non-repudiation. The focus right now is to shift from confidentiality to authentication and non-repudiation. But now you're aware that RSA actually and asymmetric encryption algorithms can help out with that, especially RSA. So remember Bob and Alice. So we talked about then to kind of wrap up. So the limitations of symmetric encryption. The fundamental limitation of symmetric encryption is how do two parties agree on a key? In order for Alice and Bob to communicate securely, they need to agree on a secret key. So it's a whole chicken and egg problem. And this problem, as we have stated, is especially common in the digital age. We constantly end up at websites with whom we decide we want to communicate securely, like online stores, but with whom there is not really an option to communicate offline to agree on some kind of secret key, right? And that's what we use RSA for. In fact, as you know, it is all usually done automatically, browser to server, right? And for the browser and server, there's not even a concept of offline. They only exist online. So you need to be able to establish this secure channel. So asymmetric encryption, we have the two parties. Remember, there's 4 keys total. Bob has a public and private. Alice has a public and private. Each party has their own public key, which they share with the world, and their own private key, which they keep secret. Okay, and then we covered this already, and we looked at this diagram, so that make sure you understand this really well. So let's see. Oh, yeah, sorry. It's a little bit repetitive, but it does make the transition. So it's impossible to overstate the importance of this. Alice and Bob do not need to plan anything ahead of time to communicate securely. You just create your public and private key, and you're able to do the whole communication. They generate their public and private key pairs independently and happily broadcast their public keys to the world at large. Put it on your web page or something. Alice can rest assured that only Bob can decrypt the message she sends because she has encrypted it with Bob's public key, right? So remember, that's for confidentiality. Yes, he's received a message only he could read. And the message claims to have been sent by Alice. So this is where now it's kind of flipping the to authentication, right? So yes, he received a message only he could read, and the message claims to have been sent by Alice, but he has no guarantees that it really did come from Alice. Do you see that? So that's now the current problem. So now we're going to build an infrastructure where I can ask you, do a demo where in one shot you achieve both confidentiality and authentication. Do you see that in one single email? And you're able to build that. You just have to understand the sequence of steps that you need to follow. Okay? Some public key cryptography algorithms, including the RSA algorithm, have the special property of being commutative, which means that the roles of private versus public key are interchangeable. And by interchanging them, we can now do from confidentiality move to authentication. Therefore, Alice could encrypt a message with her private key that is decryptable only with her public key, right? Since everyone knows her public key, you may well ask what the point would be, right? And that's what we've mentioned. It's kind of strange, right? So if you're just thinking of confidentiality, it makes no sense. Everybody can look at this message. But we're considering the other idea of authentication. This message would be readable by anyone, but only Alice could have created, because only her private key produces messages decryptable by her public key. Do you see that? And so that's the key. Obviously, we do this on the hash value because it would be really hard to like interpret text that's coming out, right? So we don't want to do that. So this provides a form of authentication, a really powerful one that the whole internet is built upon. So if Alice's plain text message is M, and she first encrypts M with her private key, okay, then with Bob's public key, Bob can take the message he receives and decrypt first with his private key, and then with Alice's public key, and he'll recover M and achieve both confidentiality and authentication. Do you guys understand? Does this make sense? Any question? All right, good. So yeah, so that's it. So the guarantees are that only Bob can read the message and only Alice could have sent this message. So that's one way of doing it. And this way doesn't have integrity in the loop, but that's fine if the goal is just to read the final message anyway, right? So you can also add integrity in there. So here's the graph. Make sure you understand how to do this, because this will be one of the questions that I will ask on the demo, right? So you're going to work with your partner as usual. You'll have all the keys that you need from VM to VM, and you're going to be exchanging the messages via email. Okay, so that's essentially. So, I may ask you to do this. So, assume you're Alice. You start with your plain text. You encrypt with Alice's private key. You're Alice, so you have access to Alice's private key. That creates one cipher. Let's call it cipher 1. Then cipher 1 is encrypted with Bob's public key. That's for confidentiality, right? So that in the exam, I could also ask questions like this. If we do this here, what is this for? Authentication or confidentiality? And then over here, is it for authentication or confidentiality? So you have to understand why we're doing something. So cipher 1 is encrypted with Bob's public key, and now it becomes cipher 2. At this point, you're going to send it over the insecure internet. Cipher 2 arrives on Bob's, side of the world, and then Bob has to decrypt it with Bob's private key, right? That's the confidentiality part. That produces a cipher 1, and then cipher 1 is going to be decrypted with Alice's public key, which Bob will have, and now it produces the plain text message for Bob to read. Okay, and you achieve both confidentiality and authentication in one shot, but not integrity. All right, so let's take a look over here, just a few final thoughts, and then we can switch over to the notes. So public key encryption structure. So it was proposed by Diffie and Hellman in 1976. So that's why Diffie and Hellman still used sometimes, not as popular as RSA, although it actually, I believe recently it like regained like they made an improvement and it regained use. So it's still out there. But this was the original proposal in 1976 based on mathematical functions. We'll take a look at those probably next week. But anyway, asymmetric encryption here in general, we use two separate keys, a public and a private key. Public key is made public to others. All right. So, and yeah, so that's the idea. This should be the framework, just to finalize it. We have the plain text message from Bob, X. We have an encryption algorithm, which is RSA, that function that you guys know, M to the E mod N, right? And then notice we have a whole bunch of keys in our environment of our friends or colleagues. These are going to be their public keys because we are trying to achieve. Notice down here it says directed toward providing confidentiality, right? So we're going to use, let's say, Alice's public key to encrypt, send it over the insecure internet. Then the decryption algorithm, which we also know, is at Alice, so she uses her private key, and now we obtain the message. Okay, so that's that scenario. Questions on that scenario? All right, now the contrast for authentication. Notice down below this slide says directed towards authentication. So here, Bob again takes the plain text message, has an encryption algorithm RSA, but now Bob uses his private key, sends it over the insecure internet. Alice has the decryption algorithm, and she is going to have Bob's public key, the corresponding one, so she can decrypt the message, and this achieves authentication, essentially. So anyone who knows the corresponding public key will be able to decrypt the message. So essentially everyone, because it's a public key. All right, so here are now the three asymmetric algorithms. We've spent most of our time so far with RSA, but we're as far as algorithm descriptions, but we'll be moving the next to Diffie-Hellman. I will skip DSS, but we will cover a little bit of elliptic curves as well. And elliptic curves are similar to RSA in some ideas, but you just have to imagine that there's this universe, and this universe is governed by a function, which is like a geometrical shape. That's why it's called an elliptic curve. It's like a curve, a shape. Like if you had a circle or you had a triangle, and there's a set of operations that are not like normal math operations. They're only geometric operations in that space. And so what we have given that curve and given those operations is that we use them to extract numbers in a similar way to how we extract the prime numbers for RSA. And then after that, there's similarities in the algorithm. You see that? So that's really what it is, but we'll see that later. And there's a few well-known curves that are considered to be secure, and there's a lot of other curves that are candidates but not guaranteed to be secure. So for instance, the blockchain uses elliptic curves and is based on one specific, very well-known elliptic curve that has been studied extensively. Okay, so these are the ideas. It's kind of where the numbers are coming from, but we'll see that later. So we have our goals are digital signature, symmetric key distribution, and encryption of secret keys. So RSA can do this. Diffie-Hellman has some limitations in the past in particular, and elliptic curves also today are very popular and considered, like an advanced, a slightly more advanced technique. Okay. But yeah, these are the three important asymmetric algorithms, essentially for key exchange. So requirements for public key cryptographic systems. It should be computationally easy to create key pairs. Okay. Computationally easy for sender knowing public key to encrypt messages. Computationally easy for receiver knowing private key to decrypt the ciphertext. Remember that usually these are only for small things that we're encrypting, right? So that whole Netflix movie, you want to use symmetric encryption, not asymmetric. These are computationally infeasible for the opponent to determine the private key from the public key. So that has to be very hard. Computationally infeasible for opponent to otherwise recover the original message, right? And useful if either key can be used for each role, right? So that, also authentication and confidentiality. Okay, so here's just a few ideas. Uh, RSA, as we've discussed, been around for a long time. One of the most studied algorithms in cryptography, one of the most powerful, still in use. I mean, there's always like competition but it's still very powerful. Developed in 77, most widely accepted and implemented approach. Elliptic curves, also known as ECC, security like RSA, but with much smaller keys. So that's kind of one of the incentives, right? So this problem that RSA requires these massive keys of 4096 and beyond. So you'll see that elliptic curves is still as secure with things that are smaller, so that computationally it becomes more feasible. Does that make sense? So that's one of the, it's not, hopefully by now you have seen in this course that it's not just about security, right? Cryptography also is about performance. It has to be fast enough. Otherwise, it's not as useful. All right, and that's the other set of slides that I wanted to cover. So I've covered both, and then I just have a few notes left, and that's it. That would wrap up the theory of RSA as we start moving into the other algorithms. But like I said, we're going to continue to use our like for applications. So really just the theory ends here. But we're going to continue to exchange keys and authenticate. You still need to do digital signatures, and there's a homework coming up on digital signature. All right, so I'm done with my slides here. Okay. So now I have a few last notes, a few kind of last little ideas that I want to cover, and that should take 20 minutes or so, and then we're gonna go back to the VM to finish up with PyCryptoDome, right? And I'll probably introduce the RSA set of algorithms as well. So I think this module is done. So this one is done. And now we are at this module, PyCryptoDome, right? So we're going through the code. I'll assign a homework this Thursday on this one. But let's now switch over to the whiteboard, and we're just going to cover a few last concepts of RSA to wrap things up. So I'm going to click on whiteboard, new whiteboard, classic. Or just give me a second. There it is. It's always like a random thing, and eventually it works. Okay, so here we are. It's working. Yeah, so just a few little thoughts here. So let's take a look at how the numbers are related to binary, for instance, right? So this is really important because of this operation, m to the e or c to the d. This is massive, right? And so you want to find as many efficiencies as you possibly can. And as it turns out, at the binary level, there are advantages to having something that might be like this versus something that is just like that. Do you guys see that? And so I'm just going to give you a brief intuition on this idea. So for instance, why do they prefer that number for E? What was that number? Like 53,000. Yeah, 65,537, right? Why is this preferred as the E? Well, because first of all, it's secure enough. It meets the security parameters, but also because when you convert this to the binary, it has certain characteristics so that it's faster. And so once again, you have this balance between security, but also performance. These are highly optimized things. Do you guys see what I'm saying? So for instance, let's imagine the scenario where we have P and Q, right? So P and Q are going to be 197 and 211. So in this example, we can represent these as binary. So it should be something like, so P is 197, which should be 11000101. And then you have Q, which is 211, which would be 11010011. Do you see that? So you guys know how to do this already because you know how to convert from binary to decimal, right? So essentially that's what this is happening here. So you're saying that this is 2 to the 0 plus 2 to the 2 plus 2 to the 6 plus 2 to the 7, right? So if we do these, that should be what? 128 plus 64 plus 4 plus 1, right? And if you add this, that should be 197. Do you guys see that? So the whole point is that these numbers, like in this case, this number is selected because it has certain characteristics at the binary level. Okay. And that just because of this operation of m to the e, mod, what is it? Mod n, this, is computationally expensive as we have seen. So you want to encrypt with a more efficient number, right? So that's just something to consider. Another thing to think about is the n that is generated. So in this case, when we create n, p times q, well, this is going to be 197 times 211. So this produces an n which is equal to 41567. And this actually will require 16 bits instead of 8 bits to represent it. So the corresponding number for 41567 would be 1010001001011111. Okay, so notice this has 816 bits to represent the n. Okay, so okay. So we have seen here the bit pattern for the chosen P and Q and the modulus. As you can see, for a 16-bit RSA cipher, we have a modulus that requires 16 bits for its representation. Right? And so that, as I said, this is one of the reasons why this number E is selected, both for security, but also for performance, because its representation is just a little bit more efficient. So that's where that comes from. Any questions about that, guys? So it's the E that meets the security, but also it's going to give you that speed up that you want here in this massive computation. All right. So this one, I'm not going to repeat the whole thing, but we would calculate from these, phi, E, and D using the algorithms that we're familiar with. That's one thing. So notice here's the definition. So for computational ease, one typically chooses a value of E that meets the conditions of, for RSA, the GCD, and that has as few bits as possible equal to 1 for fast multiplication. That's the definition, right? And at the same time, that is cryptographically secure in the sense of RSA. So ultimately, this is a very common number that you'll see a lot that meets those conditions of security and efficiency. Okay. So that was the issue with E equals 65,537. And then the last thing that we're going to cover now is the representation of, let's say you have, before we've been encrypting just one number, right? So if you remember, I gave you M equals 65 and I asked you to encrypt that. But obviously you may want to know how you can build from scratch your own algorithm for, a whole sequence of numbers. Okay. So let's imagine here, I'm going to set up a problem. Or that. So we already know the algorithm. I'm not going to repeat the algorithm. I'm just going to give you the values and we're going to go through it. And this is the last RSA problem. So let's say that we have a message. We have a message M, and it's essentially maybe hexadecimal. It's going to be some kind of a secret key made up of numbers and letters. So you might want to use the ASCII table, for instance, to convert those numbers and letters into actual numbers, right? So you're going to convert them like we did in the first substitution cipher, for instance, where we used the ASCII table. And I think like we had like, let's say N was 72, M was 73, something like that. Do you guys remember that? So you can assume that you start with the ASCII table and convert to numbers. So then you just have to have a convention that every 2 or 3 numbers is a letter or character. So let's suppose in this example that I'm going to do, I'm going to assume a block size of 3. So suppose a block size of 3. Remember, this block size is in relation to RSA and all these numbers that we're going to encrypt. Okay, so we're going to have an original message. So we already went from the text, ran it through the ASCII table, and now we just have numbers. Okay, so we're going to encrypt the original message M, which is going to be 68832 687 9 3 sixes 666 2 8s. So now, however you did it, 4 numbers for a letter, 2 numbers for a letter, it doesn't matter, right? You created this sequence. You want to come back to that sequence, and then you'll have your functions that take you back to the text. But we're starting here at this. Now we create another block size of 3 for this encryption. And we just have to be consistent. So we're going to assume these to be our blocks, okay? And so now what we want to do is we want to use RSA to encrypt these messages. So we're going to consider some parameters. Okay. So, just to have a complete set of problems or values, and you can maybe replicate this in Python if you'd like. So P equal 47, Q equal 71. You know how to compute N, so I'm just going to skip to the final value, which is 3337. Then you have phi, which is going to be, you know how to compute it already. So I'm just going to skip to the final value, 3220. Okay. Then, as you know, we have to use the algorithms that we discussed in previous lectures, right, to calculate E. So, the GCD and less than phi. So we're going to select an E equal to 79. Okay. And then we compute D, the D exponent. And you know also how to do that already with Python and through the formula. And that's going to give us 1019. Okay. So once you have these parameters, you agree that your public key is equal to, who can tell me what the public key is actually? What would be the public key here? 79 and then what? 1019. Oh no. If you do that, you have made your private key. 337. It's 337, yes. Yes, be careful with that. All right. So who can tell me now what the private key would be here? What's the private key? I could give you this problem on the exam, right? So it's like a nice one. What's the private key? Oh, sorry. Yeah. Very good. Yeah, exactly. Right. So now we have all the parameters, and now we're going to proceed to encrypt. We know that our blocks are of size 3. We stated that. Okay. Okay. So because I need more space, I'm going to switch to to the next slide. All right. So now we're going to proceed to encrypt this message. So how would you do it? It's pretty simple. You just encrypt every block individually. Guys, do you have any questions? So the first block was 6888, correct? So then we do, 688 is the block. So we proceed to encrypt that. So 6888 to the 79 mod what? 337. And that will give us 1570. Do you guys see that? All right. Then we do the next block, which is 232. That's the next block. This is plain text. Remember, this is all plain text. So I do 232 to the 79 mod 3337. and that's going to give me 2756. Okay. Then I do the next one. Notice they're basically independent. So the next one is 687. So that's going to be 687 to the 79 mod 3337. And that's going to give us 2714. Okay. Then the next one, we just have two more. The next block is 966, right? 966. So we take 966 to the 79 mod 3337, and that gives us 2276. And then the final one is the same 6888. If you notice, it's the same block as the first one over here. So it's 688. That's going to be 6888 to the 79 mod 3337, and that should give us 1570. What do you notice about this? Blocks of 3 generated consistently what? Blocks of 4. Do you see that? So this is very handy, right? Because they're all of size 4. Pretty interesting, right? So the encrypted ciphertext becomes, of size 4. So note that each block of 3-digit plain text becomes the block of 4-digit ciphertext. Okay? And that is the message. So you can now create the cipher 1570 2756 2714 2276 1570. So what do you remember about symmetric encryption? We were just XORing, right? So we had a plain text that was a sequence of bits, and then we would generate essentially the cipher, which had a consistent size. Whereas here, what do you notice? The ciphertext becomes bigger than the plain text in this approach. Got it? And so now that we do this, then we can proceed. And in this example, I'm not going to do all of them, but now you send this. So this goes, Bob sends this over the insecure internet to Alice. And now Alice is going to take this number and decrypt it back to the original. And that's essentially how you can do the actual RSA. You can do everything by hand. So let's take a look at that process. So now we're just going to reverse it. To decrypt, right? What do? We're going to take the original message, which is 1570 2756 2714 2276 1570. And we decrypt it, as you guys know already. So how do we do that? Let's say 1570. It's going to be 1570 to the what? To the 1019, right? The decryption exponent. So imagine this is pretty big, 1019. Big computation there. Mod, the same N3337. And if you do this, and I encourage you guys to repeat this exercise in full in Python, just so that you can actually do it. I'm not going to assign it as a homework, but you can try it out. And this should give you 688, which if you remember, was the original 688. So now you've decrypted the message back. Got it? And so this is how you can go from these. So I'm just going to do, I'm going to skip to the last, well, the last two, I guess. So 2276. And the last one was actually 1570. So it's the same. So this is 2276 to the, this is dot, 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 1019 mod 3337. And that would give you the 9666, right? And you've gone back from blocks of 4 back to your blocks of 3, which was the original plain text message once we converted it into integers. That's it. So let's do for completion the last one. So 1570, so it would be 1570 to the 119 mod 3337, and that is 688, another block of 3. And now you just put it together, and that's it. So now you have the ability to, from scratch, encrypt any message of any length, and do this. Keep in, one important point here, for instance, if you were doing this for a whole movie, you effectively just made it way bigger, right? So that's kind of the idea. So the key size of RSA, it's usually pretty big. 512 bits, which is something that we used, is no longer considered secure in practice. However, it is still effectively impossible to crack something like that in a very quick fashion. The other thing to consider, remember that Python is not a fast language. All the examples have been done in Python, but something like OpenSSL, for instance, is written in C, C++. And C, C++ is the fastest computer language. So anything that you write in C, C++ will run super fast. So obviously, what you're seeing in Python, if you were running it in C, it would be much faster. So obviously, in today's world, we're going to use something like 24 or 4096 bits for the size of these keys. All right, so a few just final comparison, and we'll wrap up there between DES and RSA. DES and RSA. So DES, you should know, or AES. This is symmetric key encryption. So this is for like confidentiality, encrypting the message. RSA, remember, is for sending the key. So as far as speed, DES is 100 times faster than RSA. Okay, so it's 100 times faster, way faster, right? That means that obviously RSA then is 100 times slower than DES, right? So 100 times than DES. So again, there's this duality between security, but also performance. We use, so remember this is for pub. We have 2 keys, public and private. This one only has 1 key, the secret key. Okay. Now, and the last one here is the cipher text size, which we just did, but I'm just gonna state it here. Cipher text size. So we take, the block, plain text block, encrypt it with a key. We XOR it. Essentially, it comes out to the same. So cipher text has the same size as plain text. Here in Des, you could say for each block, oops. Say cipher text is same size as plain text. In the RSA case, as we just saw in the example, ciphertext becomes larger than plain text. And you guys just saw that. It goes from blocks of 3 to blocks of 4. And keep in mind, we're using fairly small n and all of that. So what's the compounding effect of that? Do you guys see that? So I'm just, I'm trying to put the idea in your heads that there's this balance between performance and security, and RSA should not be used for actual encryption. All right, so that's the RSA algorithm. So that concludes that part. We still have some time. So let's go ahead and switch over to the virtual machine, and we're just going to continue with the code. But, good thing we finished RSA. So that's finished. Okay. The next algorithm to cover, probably Diffie-Hellman or elliptic curves. But for this, for the rest of today and Thursday, we're going to continue with PyCryptoDome and just build those functions. So let's go ahead and switch over to the VM. So I'm going to do share. Share the screen. All right, we're going to start the VM. And we're going to try not digital signatures today, but let's just try to do some things related to RSA. Like we have some functions, right? Generate keys, and then encrypt and decrypt. Start. So all of this is on the GitHub already, all these scripts. So you can get them from there. Just go to the cryptography folder, and there should be a subfolder in there called PyCryptoDome. We already installed PyCryptoDome last week, and we already did the AES encrypt and decrypt functions. So that should be working. We still have to cover how to create a digital signature, and then how to do RSA, basically encrypt and decrypt and generate the keys. So let's try. Yeah. So we're going to start with this process. This is going to be simpler, remember, with PyCryptoDome because we're using libraries. So we just like almost magically say, create a public key, then from this, create a private key, write them to a file, right? So that's essentially where I'm going to start today, where I'm going to lay out the function. And remember, I'm keeping these as little separate scripts. So I strongly recommend you create a folder just called PyCryptoDome with all the individual scripts in there, okay? Okay. All right, so let's log in. And all right. Yeah, so we'll just do one function and then we'll wrap up here with this gen RSA one. But this is actually very useful because we're going to save these to text files, these keys, and so now you'll have these text files and you'll share your public key with your partner, and this is the key actually that you have to send them, right? And then you're going to keep your private key. I strongly recommend that because you're going to have your public key but someone else's public key in your environment probably, I recommend that you name them, like, you know, Matt public key, Alice public key, right, in the text file itself. All right, I'm just waiting for this to. All right, so let's open the terminal. Here. So ls-l, we're going to navigate to the desktop. We're going to find our full 2025 folder. And we're going to go, I have a folder called PyCryptoDome My. I'm going to go there. /L. All right, so if you remember last week, we went over AES, encrypt and decrypt, and we did everything related to that. So now you have a way of encrypting a message, right? We even created a secret key, and the secret key is stored in this file in plain text format. Now we need to establish the functions for RSA that will let us grab that key, encrypt it so that we can send it securely over the insecure internet. But before we do all of that, we need to create our keys, our public and private keys. So instead of using the whole P and Q and then N and all that, since we're just using a library, we're going to have these handy functions that do all of that for us. This script, you really just need to run once when you're working with your partner, and that's it. You have your public and private key, and you don't need to use it again unless your keys were compromised. Do you see that? And then you have to do the exchange again. So let's create this function, which I'm going to call gen RSA keys, nano gen RSA keys.py. Okay. Since we're using PyCryptoDome, we just use the library. So from crypto, notice now instead of AES, I'm going to use dot public key. Notice this K is uppercase. And from here, we're going to import RSA, just like that. Then I'm going to use from crypto. So from crypto import random. Okay, just like that. All right, so we need to create a key. The key, this is very straightforward. You just do key and you do RSA dot generate. And you specify the size that you're going to use. So in this case, 2048. So secure, right? So secure key. Do you guys see this? All right. And once you do that, that's your key, but your public key. Now from here, you extract the private key, which is also in there, but you have to more explicitly extract it. So I'm just going to say private key, and that's going to be equal to just grabbing key dot export key. Just like that. Now the naming conventions and things like that, this started as an open source crypto library that was later more people came and improved it, but it's a little bit not as professional as some others, so the naming conventions are a little strange. Just be aware of that. Again, I can't say that this is a secure implementation. If you want security, stick with OpenSSL, right? In Linux. But it's robust. So that's it. So once I've done this, what do I want to do? Now I want to save these keys into text files because obviously that's what you're going to be sharing with your partner and everything. And that's really key, really important. So let's do that. And then we'll look at the outputs and that'll be it for today. So let's print out the files. So usually whenever you're dealing with keys, the extension is called a .pem file. So we're going to use the same extension as these are consistent with the same PEM format used by OpenSSL. All right, so let's create file out. This is the file handler. So we're just going to open a file. We're going to call it, this is going to be the private key. So I can call it private.pem. I do strongly recommend that you use your name, your partner's name, so it's easier to identify what it's from. So private pem, and then because these are binary, if you remember, we're writing, so WB, right? So we'll write binary. So then we do file out dot write, and what do we write? We're going to write here the private key like that. And then we can go ahead and close this file. So we're just going to say file out dot close, just like that. And that creates the file, the PEM file for, our private key. We just repeat then the same thing for public. So over here, I'm going to do the way that this works is like this. You do public key, and that comes from key dot public key like that. I think I'm missing. Yeah, so yeah, it's one word. So key dot public key, and then you'll say export key. So dot export. Okay. So now you have the public key also. All right, and then we should be ready to write it out. Okay, I don't see any typos. So now we create the file for this. Same thing, file out. File handler, open. This is gonna be the public. So we call it public.pem. And we're going to write bytes, so WB. Then we do file out dot write. And we write public key here. Is that variable that I just created. And then we just close. File out. And that's it. So if everything is correct, once I run this script, I'll be able to create a public, a pair of public and private keys with a size of 2048. So, pretty good. And now I can use these to exchange this AES key securely. So let's hope it works. Let's try it out. All right, so let's do an ls-l here as you can, ls-l, as you can see, there's no public and private keys yet. So we need to run this. Perfect, right? So no errors, took a bit, as you saw, there was a lag there. Now we do ls-l. We do have two PEM files. Notice that the size of the private key is larger than the size of the public key. Okay, so let's do a clear. And now we want to visualize these two files. So we can do cat public. And there you go. That's your public key. Okay, so when you're working through the problems, and if you notice, it's the PEM format that OpenSSL also generates. So it's the exact same one. So you will send that to your partner, right? So for you to, as you work through the problems of achieving authentication or confidentiality and so on, these are the files that you will send. Now, if you remember, we can't really tell from what we're looking at there, but that's your E, N. They're in there. Believe me, they're in there. So in a future lecture, I'll show you the OpenSSL commands so that we can take that file and make it a little bit more readable so that we can actually identify E in it. Okay? But this is actually how it is. The standard is exactly like this. All right, now let's take a look at the private one. So I'm going to do private PEM, private.pem. And you can see it is much bigger, of course, and it's called the private key. All right, so these are the two files. So now everyone has the capability of creating their public and private keys that you can use, for solving all the other problems. Does this make sense, guys? So remember, you only need to run this script once, then kind of put it on the side, and then, I still need to give you all the encryption and decryption things. We're going to do that on Thursday. So in Thursday's lab, I will continue giving all these until you have everything, and then you can start solving through the problems. Any questions for me? All right, guys, so we can stop here for today, and I'll see you guys on Thursday to continue this lab.